Hello all, and welcome to the next session of the course Pre-MBA Statistics. Now we are entering a very fresh week, and as you see in front of you, the whole focus of this week, at least in the first couple of sessions, would be sampling distributions and estimation. Now again, this entire idea about estimation, I'll try to break it down as in how we'll progress into this week. But estimation is a key that once you understand the distribution of the data set, let's say being normal distribution or exponential, binomial, Poisson. So once you sort of have a practical data set and sort of fixate a distribution on that data set, then the next immediate important step is to estimate the underlying parameters of the distribution. So just to give you a very quick example before we begin with the slide. So let's say if the distribution happens to be normal mu sigma square. So just pause the video and try to answer a simple question that how many unknown parameters do you see here if the distribution is normal mu sigma square? So the answer is 2, right? So one of them is the mean, which is mu, and the second one is the variance, which is sigma square. Now this entire idea about estimation is we are sort of assuming that the entire population and the parameters of the underlying distribution are unknown. So both these parameters are assumed to be unknown, and hence depending on whatever data set you collect or whatever practical data you collect, we have to sort of estimate or get an idea about what the values of the unknown parameters would be. Alright, so this is a fairly simple idea about estimation, or rather estimating the unknown parameters of a distribution. But the other aspect just before we enter into estimation is sampling distribution. So we'll start with kind of extending a normal distribution and then see a couple of other distributions which are again very standard, widely applicable in, let's say, regression or hypothesis testing, confidence intervals, etc. Okay, so I'm very sure that many of you might have heard about the term t-test, okay, or a chi-square test or a z-test. So all these distributions, let's say t distribution, chi-square distribution, of course f distribution. So if you transition into regression, we have ANOVA, which is called as analysis of variance, right? But the underlying distributions are, let's say, t, chi-square, f, and these three distributions are called as sampling distributions. And we'll see exactly why are they called as sampling distributions, okay. But again, just a quick refresher that all these three important distributions t, chi-square and f are kind of extensions of normal. Now again, extension of normal may not be the correct word here, but we somehow play around with a normal distribution structure and then try to derive the t distribution, chi-square distribution and f distribution, okay. And then we slowly transition into what is called as estimation. So again, within estimation you have two kinds of estimation: point estimation and interval estimation, alright. Okay, so as discussed, we'll start with sampling distributions from a normal population. Now again, the underlying assumption throughout this entire session would be that the distribution itself is normal. So the population is supposed to be distributed as a normal distribution, alright. So let's see what's written here. So let x1, x2, x3 all the way up to xn be a sample from a normal population having mean mu and variance sigma square. And again, we can sort of assume that they are IID. So what do you mean by IID? So identical and independent and identically distributed. So IID, okay. So this entire set of random variables are IID, and they're sort of coming from a normal distribution or a normal population having mean mu and variance sigma square. Now as always, we can define very quick sort of summary variables. So the first one is x bar. So what is x bar? So x bar is nothing but the sample mean. So simple average of all these n variables here. So you simply take the summation xi divided by the number of variables you have. In this case, it's n. Alright. So x bar is nothing but a usual or a standard sample mean. And on the other hand, we have s square. So s square is nothing but the sample variance. Okay. Now just a subtle difference between the formulas of population variance and the sample variance. So always remember that whenever you write down the formula for a sample variance, you have n minus 1 in the denominator and not n. Okay, and again you have a subtle idea about degrees of freedom here. So again, there is no point of talking about degrees of freedom at this point. So maybe sometime later we can talk more about that. But just to understand that we have to take n minus 1 rather than n in the denominator. And one very quick sort of a property of this s square is this s square happens to be unbiased for sigma square. Now again, from last couple of sessions, if you know what you mean by unbiased, or probably we'll discuss what you mean by unbiased very soon, but unbiasedness means that on an average the value of s square happens to be sigma square. So expected value of s square happens to be sigma square. So if you had written down n in the denominator, this property would not have held true. Okay. Anyways, but then before we start with sort of deriving the sampling distributions, we have to sort of rely on these two important summary variables, so x bar and s square. And of course, the last statement is what we have been saying all this while, that x bar and s square denote the sample mean and sample variance respectively of whatever random sample x1, x2 up to xn you are collecting. Okay, so now the very first thing is, before we transition into t, chi-square, f, slightly advanced distributions, you have to sort of understand that what is the distribution of the sample mean itself. Now again, remember a very subtle point, that if you are collecting data and then if you have a set of random variables x1, x2, x3 up to xn, and each one of the xi's are a random variable. So of course you take x bar. So x bar is what? X bar is nothing but the average of all these n variables. Okay. So if all these individual variables are random variables, then most certainly this sample average or the sample mean is also a random variable. And the moment you say that any quantity is a random variable, we can sort of find a distribution for that. Okay. So this entire slide sort of gives you a distribution of the sample mean. So a very important property, I'll probably star it. So since the sample mean is a linear function of normal variables, now again remember, how are you finding the sample mean? So sample mean is nothing but summation of xi divided by n, isn't it? So summation xi by n is nothing but my x bar, and the moment you're talking about sum of xi's is nothing but a linear function of several individual normal variables. So hence the overall sample mean, which is x bar, is nothing but a linear function of normal variables. And hence, from a property that we discussed when we discussed normal distribution, is that any linear function of a bunch of normal variables is also a normal variable. Okay. So hence, the important property from this entire slide, or the crux of the matter, is that the distribution of x bar itself is a certain normal distribution. Now the only thing which is important and remaining is finding out the mean of x bar and variance of x bar. Okay. And here we sort of delve into certain properties of expected values or properties of expectations. Okay. So to find the mean of x bar, we simply take the expected value of x bar, which is the first equation that you see here, and this is nothing but the expression of x bar, and I can sort of take the expected value inside the summation sign. So this would be summation e of xi. N in the denominator is a constant, I can bring it out. So overall it will be 1 by n summation e of xi. Now again remember, how are the individual xi's distributed? So again, you may pause the video, you can sort of digest what's going on here. So again, from the last slide, we saw that all these individual xi's are nothing but normal mu sigma square as per the assumption. Okay. So each and every individual expected value of xi should be mu. Okay. And then how many such mu's are you summing up? You're summing up n such mu's. So it will be something like n mu divided by n here, and then you can cancel out the n, and then answer happens to be mu. Okay. So ultimately, expected value of x bar is nothing but simply mu. Alright. And on the other hand, we can sort of also prove that if you take the variance of x bar, so variance of x bar happens to be not sigma square, but sigma square divided by n. And this is, I'll say, a very important property. You should always remember these two quantities pertaining to a sample mean of a normal population, or random variables which have a normal distribution, and then you're talking about the sample mean and the distribution of the sample mean. Okay. So again, just to understand, the distribution of x bar is nothing but normal, where mean is mu, but variance happens to be sigma square by n here. Okay. And thus, a step ahead, we can sort of standardize this further, isn't it? So we can subtract the mean divided by the standard deviation. So something like x bar minus mu divided by sigma by root n. So we can sort of have x bar minus mu divided by sigma by root n, and this happens to be a standard normal distribution. Okay. So again, remember, how do you derive a standard normal distribution? We have to standardize a normal variable. So we have to subtract the mean, which is mu in this case, and divide it by the corresponding standard deviation, which is nothing but sigma by root n, and the underlying distribution happens to be a standard normal or normal 0, 1 distribution. Okay. So again, I'll say that if you sort of get a hang of how you're taking expectations over summations, how you're sort of taking variances, then simultaneously the things will be slightly easier to understand when we sort of derive, let's say, a t distribution or a chi-square distribution, etc. Alright, now the second important distribution is called as a chi-square distribution. Now again, like I said, all these important distributions, be it chi-square or t or f, are sort of derived from a normal distribution, and hence they are called as sampling distributions. So again, sampling distribution means what? So sampling distribution means that all these quantities, right, x bar, s square, or any function of, let's say, your original random variables x1, x2, xn are called as sampling variables. For example, x bar is called as a sampling variable, s square is called as a sampling variable. And then on top of that, we're sort of focusing on distributions of all these sampling quantities or sampling variables, and hence the underlying distributions, be it chi-square or t or f, are called as sampling distributions. Okay. So hopefully the idea should be clear that first, sampling distribution means what? Again, just to summarize very quickly, is that all these quantities are sort of derived from the original set of random variables x1, x2, x3 up to xn, and hence all these are called as sampling quantities. Okay. So be it x bar or be it s square or any other function of xi's are called as sampling quantities, and when you are talking about distributions of these sampling quantities, such distributions are called as sampling distributions. Okay. Alright. So now the second important distribution is chi-square. You might have heard about, let's say, chi-square goodness of fit test or chi-square test, to check for variances and so on and so forth. So this is exactly the same chi-square distribution. So firstly, how do we derive a chi-square distribution? Okay. So again, like I said, all these distributions are sort of derived from a normal distribution. So things have to start from a normal distribution to begin with. So let x1, x2, x3 up to xn be a sample from a normal population having mean 0 and variance 1. Now we are sort of focusing on mean being 0 and variance being 1. So again, you can pause the video and then try to think that what exactly is the name of the distribution here. So the name of the underlying distribution is a standard normal distribution. So mean is 0 and variance is 1. Okay. Now moreover, the important part is how do you derive or how do you sort of visualize a chi-square distribution. So if you now take a summation of the squared quantities of each and every xi here. So summation xi square. So the summation xi square would mean what? So x1 square plus x2 square all the way up to xn square. And again, remember all these individual x1, x2 or to be more specific xi follows which distribution? A standard normal distribution. Okay. So then if you talk about summation xi square follows a chi-square distribution with n degrees of freedom. So this n that you see here is called as degrees of freedom. And again, sort of intuitive that how do you sort of put forward that n there? So how many squared terms are you summing up here? Okay. So what is the answer to that? So how many squared terms are you summing? You're summing up n squared terms. So hence the degrees of freedom has to be n here. Okay. So this is one connection between a normal set of distributions or normal random variables and a chi-square distribution. So if you start with, let's say, a set of standard normal distributions, and if you simply take summation xi square, then summation xi square follows a chi-square distribution with degrees of freedom n. Now on the other hand, one can also show that if you sort of formulate this quantity, so n minus 1 into s square divided by sigma square. Now again, what is s square here? S square is nothing but the sample variance. Okay. So if you do something like n minus 1 into s square by sigma square, this also follows a chi-square distribution, slightly different degrees of freedom, so n minus 1 degrees of freedom. But these two are kind of standard connections between, let's say, how do you derive a chi-square distribution from a set of normally distributed variables here. Okay. Now again, like I said, this s square is nothing but s square means sample variance of all these xi's here. Okay. So initially you have to begin with a set of normal variables to begin with, and then s square is nothing but the sample variance of all these n variables, and this is nothing but the derivation of chi-square. So if you have s square in place, you multiply that by n minus 1, you divide by the unknown sigma square, and this entire quantity follows a chi-square distribution with n minus 1 degrees of freedom. Alright, now moving ahead, the second important distribution after, of course, chi-square or we started with normal. So normal, chi-square, then the next distribution is very important called as t-distribution. So again, like I said, many of you might have heard about t-tests, right? So t-test is sort of to compare, let's say, different means or to sort of find out if the average of a set of values happens to be a certain quantity, right? So in all these situations, we use a t-test. Now, to be able to use the t-test, the underlying distribution there is called as a t-distribution. Okay. So first, very quickly, we'll see that how do you derive a t-distribution, then a couple of properties of t-distribution, and so on and so forth. Okay. Now, imagine that we talked about a standard normal distribution, we talked about a normal distribution, we talked about a chi-square distribution. Okay. So now, let's say imagine that if you have a z. So firstly, what is z? So z is nothing but normal 0, 1. So standard normal variable. So if z and chi-square n are independent random variables, okay, so you have two random variables here. So on one hand you have a standard normal z, on the other hand you have a chi-square random variable with degrees of freedom n. So again, This notation means that you have a chi-square variable with degrees of freedom written down as a subscript, which is n here. Okay. So again, assuming that you have two random variables which are independent, on one hand you have a standard normal, on the other hand you have a chi-square n random variable, and both these are independent. Okay, and then it sort of describes here that with z having a standard normal distribution and chi-square n having a chi-square distribution with n degrees of freedom, then this is nothing but a derivation of t. So how do you sort of visualize or how do you derive a t distribution? So t with n degrees of freedom is nothing but the ratio of z, and in the denominator you have a chi-square variable divided by its degrees of freedom, which is n here, and then a square root. So again, I totally understand this is a completely technical sort of a derivation, but this is exactly how one should derive a t distribution coming from a normal distribution and a chi-square distribution. Now again, remember, how are you deriving chi-square distribution? So chi-square distribution itself comes from a normal distribution. Alright. So ultimately this t distribution is also an derivation from a normal distribution. Okay. Now again, like I said, there is no need of sort of memorizing all these derivations. The more important part is how do you sort of apply all these distributions in a practical sense. So where all can you apply a chi-square distribution? Where all can you apply a t distribution? What is the difference between a chi-square and a t distribution? Okay. But this is just to tell you that if you start with a normal set of random variables and a chi-square sort of chi-square n random variable, then how do you sort of derive a t distribution there? Alright, so ultimately a t distribution is nothing but a ratio between a standard normal and in the denominator you have a chi-square variable divided by its degrees of freedom, which is n here, and then a square root. Okay. So the entire quantity or this entire ratio collectively or as a whole is said to follow a t distribution with n degrees of freedom. So again, like I said, how do you sort of denote a t distribution? So usually this is standard notation. So t distribution, and then in the subscript you can write down the degrees of freedom. So similarly as to how you wrote down chi-square, similarly Tn denotes a t distribution with n degrees of freedom. Alright, so I think this slide is more from a practical point of view as to how do you visualize a t distribution vis-a-vis a normal distribution. Okay. So again, on the left hand side we have all these three curves, they sort of denote density functions of a t distribution. Now again, this might be a typo. Again, it's not a typo, but again, like I said, you can sort of, if you want, you can change this to small tn, because small tn is a more standard notation to denote a t distribution. Okay. Anyways, but then if you sort of have different values of n here, starting from n, then you starting from n being 1, then let's say you increase that to 5, then to 10, then each of these individual curves denote the density functions or density curves of a t distribution with those many degrees of freedom. So 1, then 5, then 10, etc. And on the right hand side you have a comparison between a standard normal density and a t distribution with 5 degrees of freedom. So again, if you want, you can change this to small t5, but then again the blue curve is a t density with 5 degrees of freedom, and the dashed curve is a standard normal density. So the dashed curve is nothing but normal 0, 1, and the blue curve is nothing but a t density curve with 5 degrees of freedom. So again, immediately you can see that even a t distribution is symmetric, isn't it? So even a t distribution is symmetric, quite similar to a normal distribution. And again, from the left hand side curve, you can see that as in how you go on increasing n. So if you start with 1, then let's say 2, 3, 4, 5, all the way up to 10, then the peakedness of the t density sort of increases. Okay. So if you sort of transition from 1 all the way up to 10, so a t distribution with only 1 degree of freedom, the peak is kind of very, very low, and similarly a t distribution with 10 degrees of freedom, the peak is kind of the highest. Okay. And you have a very subtle relationship. So as in how you go on increasing n, so as n goes to infinity, a Tn distribution sort of converges to a standard normal distribution. So if you sort of go on increasing the degrees of freedom of a t distribution, so starting from 1, 2, 3, 4, 5, all the way up to 10, then again increasing beyond 10, right? So as in how you will go on increasing n, which is df of a t distribution, so this relation holds true. So any t distribution sort of converges to a corresponding standard normal distribution. Now again, the moment you talk about any distribution, we can sort of talk about these immediate quantities. So expectation or the mean of t distribution and the variance of a t distribution. Okay. So the mean and variance of a Tn distribution can be shown to be equal to, so again, since the t distribution is entirely symmetric, the expected value has to be 0, isn't it? So again, if you go back a slide and then try to visualize these curves, So the average happens to be nothing but 0. So the midpoint of that density curve, regardless of whatever n you bring in, is always 0. Okay, so the first important property is that the expectation of any t distribution with n degrees of freedom happens to be 0 for any n exceeding 1, of course. And on the other hand, the variance of a t distribution with n degrees of freedom is this formula. So n divided by n minus 2, and since you have n minus 2 in the denominator, you should not have that quantity to be negative, otherwise variance would be negative. So we require a small assumption here that n should be at least 2. So again, from practical point of view, we always sort of meet this criteria that you always sort of have at least 2 observations to begin with. So whenever n exceeds 2, variance happens to be n by n minus 2. Thus, if you sort of have a convergence in this variance, so can you sort of spot the convergence in this variance? So I can sort of start with n over n minus 2, and then we can sort of divide the numerator and the denominator by n. So let's say something like n by n, and then n by n minus 2 by n. Okay, and then you can pause the video and then try to answer that what would happen if I sort of go on converging, or rather taking n to infinity. So what would happen? So this quantity is 1, this quantity is 1, and then as n goes to infinity, this quantity would reduce to 0. Okay, so ultimately it will be 1 divided by 1 minus 0, which is sort of converging to 1 here. Okay, and this is exactly what this statement says. So thus the variance of a t distribution converges to 1 as n goes to infinity. All right. Okay, so we've talked about sampling distributions, and then again just to quickly summarize, we've talked about chi-square, t, and its derivation from a normal distribution. Now we're sort of stepping into an entire different idea or entire different sort of arena called as estimation. Okay, and in this session we'll specify more about or talk more about point estimation. But again, like I said, you have two different kinds of estimation techniques, so point estimation and interval estimation. So we'll start with point estimation here and then sort of transition into interval estimation. Okay. So statistical inference includes drawing conclusion about one or more population characteristics. This is the first statement here. So a population characteristic is called as a parameter denoted by theta. So again, just to sort of generalize, we sort of, let's say if you bring in any distribution, so any distribution has its own parameters. For example, a normal distribution relies on mu and sigma square, so you have two parameters there. Okay, so in general, let's say if you bring in a sample x1, x2, xn, so we can sort of say that x1, x2, xn follows a density function f where the parameter happens to be theta. So the first statement or first couple of sentences is more general. So we talk about, let's say, a population characteristic is called as a parameter denoted by theta. Now, a couple of beginning definitions sort of. So what do you mean by a statistic? So all these are again important definitions. So a statistic is nothing but a function defined on the set of all possible values of the sample data. Okay, so again just to summarize, a statistic is a function defined on the set of all possible values of the sample data. So these are some examples of statistics. So x bar, s square, x1, etc. So each one of these are called as statistics. So be it sample mean, be it sample variance, or simply x1. Okay. So again just to summarize, a statistic is nothing but some function of the set of random variables you have. So x1, x2 up to xn. So if you come up with any function of all these random variables, the underlying sort of a quantity is called as a statistic. Okay. Now once we sort of have a definition of statistic, what do you mean by a point estimator? Now again, a point estimator of a parameter theta is a statistic that takes values in the set of possible values of theta. So again just to repeat, a point estimator of a parameter theta is a statistic to begin with which takes values in the set of possible values of theta. And again to begin with, we sort of denote any point estimator of theta by theta hat. So again from now on, from this session onwards, whenever you see hat on any quantity, that theta hat or any hat quantity is called as an estimator of the corresponding parameter. So let's say if somebody wants to estimate mu, I'll simply put a hat on top of that, and then mu hat is sort of an estimator of mu. But more importantly, the last statement is also important, that since an estimator is a function of the random sample, it itself is a random variable. So be it mu hat or be it theta hat or be it sigma square hat. Okay. So all these quantities are sort of statistics, or they're derived from the sample. And since they're sort of derived from the sample, so all these hat quantities or all the estimators are nothing but random variables themselves. Okay. Alright, so for a single parameter there can be many different point estimators. For example, for mu, all of the following are valid estimators. So x bar, sample median, then somebody can sort of formulate different estimator like minimum plus maximum divided by 2, or I can sort of talk about the 10% trimmed mean, etc. So all these are valid estimators of mu. So be it sample mean, be it sample median, or the third quantity or the fourth quantity, etc. Alright, now the fundamental question is, so just from the last slide you saw that if you want to estimate a quantity, let's say a population mean, we sort of have access to a lot of different estimators, isn't it? So x bar, sample median, trimmed mean, etc. So how do you compare? So how do you sort of come up with the best estimator, or which of the previous estimators you saw on the last slide is slightly better? And to answer this question, you have a quantity which is very famous, very standard, called as mean squared error, or MSE. Okay. So what is the definition of MSE? So mean squared error of an estimator is given by expected value of theta hat minus theta whole square. Alright, so we have the expected value of the estimator minus the parameter and the whole square of that. So again, if you pause the video and then try to sort of focus on this quantity, what this quantity tells you is that if you are proposing an estimator of the parameter theta, then how much error are you making? So what is the deviation between the estimator and the true quantity? So again, the answer to the previous question is to, if you come up with several estimators of a parameter theta, then how do you choose best one, or how do you choose the better one? So it is always desirable to choose theta hat which has the smallest MSE. So whichever estimator gives you the smallest MSE, that estimator is the best one. Alright. Alright, now lastly we have several kinds of point estimators. So once we sort of formulate that what do you mean by a point estimator, so you have different kinds of point estimators. So unbiased estimators, consistent estimators, then method of moments estimators, maximum likelihood estimators. Alright. So firstly, what do you mean by unbiased estimator? So theta hat is unbiased for theta if this assumption holds true. So expected value of theta hat happens to be theta. Okay. And hence from this equation we see that expected value of theta hat minus theta is hence called as a bias of the estimator. Okay. Secondly, what do you mean by consistent estimator? So any unbiased estimator theta hat is consistent for theta if its variance converges to 0 as n goes to infinity. So if you have theta hat and variance of theta hat converges to 0 as n goes to infinity, then we will say that theta hat as an estimator is consistent for theta. Then method of moments estimator and maximum likelihood estimator are two ways of sort of finding out different, two different ways of finding out different estimators. So on one hand you have method of moments estimator, which is find out by equating the population moments and the corresponding sample moments. So again we will not go very deep into how do you find out such estimators, but these are two kinds of or other ways of finding estimators. And a slightly much more standard kind of an estimator is called as a maximum likelihood estimator, which is found by maximizing the likelihood function or the joint density. So as of now we've spent some time on sort of understanding point estimation. Now in the next session we'll sort of delve deeper into interval estimation, and again with some examples from point estimation, interval estimation, etc. Right? Thank you.